Now let's talk about elimination. We've introduced a couple of times systems of linear equations, and I told you ways to look at them, and I mentioned we will be talking about systematic ways to solve linear equations. Well, that systematic way is called elimination. Now, you all have solved these types of systems of equations. We've seen an example or two here on how to solve them. I'm straight away going to go into this simpler way of writing, which is using an augmented matrix. So right here, right here is the matrix of coefficients A, which we have seen many times. And on the right-hand side, I'm going to write the vector B. And I see I have a typo here. This needs to be an 11. All right. So I have the matrix A on the left, I have the vector B, and I know that this column corresponds to coefficients for X, and this column corresponds to coefficients for Y. What is the idea of elimination? The idea of elimination is to produce an upper triangular system so that the non-zero things are within the triangle and everything under the triangle or outside of the triangle is 0. How do we get that? So we are going to start with a pivot. So this this number over here is what's called a pivot. This is the first non-zero term in the first row. Let me write that. So that would be this position really. It's not about the number itself. This position is a pivot. But what is important about pivots is that they cannot be 0. And we'll see an example of what happens if we actually have a 0 in the pivot position. So this number is not supposed to be 0. And this number will allow us to eliminate underneath it. Now, what can we do here? So I'm going to write an equation first. I'm going to write an operation and then I'll describe what I mean. So how can I get a 0 underneath that 1? I'm going to write that operation as R2 minus 3R1 going into R2. Now, what do I mean by this? So by R1, I'm referring to the first row of the matrix, and by R2, I'm referring to the second row. In the system of equations, R1 would refer to the first equation, and R2 would refer to the second equation. Now, when I write this operation, R2 minus 3R1 into R2, what I'm saying is to replace the second equation with a linear combination of the two equations. And this is something that we have typically done in trying to solve systems. So I don't have a rule that goes into R1, which means that I'm going to keep R1 as is. So I'm going to keep the first row of the system just the way it is. Now I'm going to apply this operation, R2 minus 3R1 into R2, on a term-by-term basis. So first, I'm going to do that in the first column. So I'm going to do 3 minus 3 times 1 equals 0, and that's going to go in the second row. So I will write that 0 right here. Now, in the second column, I'm going to repeat the operation. So I have R2, that's a 2, minus 3 times R1. Well, R1 is a negative 2, equals, so that is 2 plus 6, that's an 8, and that 8 goes right here. And then I'm going to do that computation in B. So I have 11 minus 3 times a 1, and that's equals 8. So now I got this simpler system. If I wanted to do this with equations, what the new matrix corresponds to is this system, x minus 2y equals 1. And then instead of 3x plus 2y, I have 8 y equals 8. Now, these two systems, so this system and this system, they are not the same. They're not the same systems. They're not equal. If you try to represent the row picture, you have different lines. If you look at the column picture, you have different columns. But what the two systems have in common is that the same x and y values solve both systems. So x and y haven't changed. So we call these systems equivalent systems. Now, once we have obtained this upper triangular form in A, so this is no longer A, we'll call this matrix U for upper triangular, and we'll call this vector C because it's changed. So we started with a system AX equals B. We applied this operation here, R2 minus 3R1 into R2. And we produced a new system, UX equals C. What is same in the two systems is X. The advantage of going into U is, well, we have a 0 there, and it's actually quite easy to solve that system using another part of elimination, of the elimination process, which is actually called back substitution. So now we solve UX equals C using back substitution. Why do we say back substitution? Well, because first we're going to solve the second equation, which will tell us what y must be. Then we'll use that y and go into the first equation to figure out what x must be. So we're going back, whereas elimination was using the first equation to eliminate into the second equation. So let's solve this problem. I guess green is fine. So the equation is 8 times y equals 8. So that tells us here that y must equal 1. And when I replace it in the first equation, I get x minus 2 times 1 equals 1. And from here, x must equal 3. And we knew this from the previous video. All right, so this is a situation where everything works out. We're able to solve the problem. Elimination is fairly straightforward. Elimination doesn't always work. So there are situations where, well, the system doesn't have a solution. Where could that happen? Well, it could happen if the two lines are, for example, parallel. Let's right away go into representing this system in an augmented matrix. So the corresponding matrix is 1, 3, that's the first column, -2, -6, equal to 1, 11. Now, again, the pivot is this number, so this is the pivot. It must be non-zero. If that was a 0, I would not be able to call it a pivot. So it is the first non-zero in a row. By the way, in the previous matrix, now in U, 1 is a pivot and 8 is a pivot. So these are the two pivots. These are the two numbers that ultimately tell us what x and y are. And we use those to eliminate with them. Okay, so we have the pivot in the first row and we want to use it to eliminate into the second row, eliminate everything under the pivot. The first row is R1, the second row is R2, and the operation that we want, well, we have to do something like this. It always starts with row 2 minus a number times row 1 into row 2. This is always going to be the structure of the operation. So R2 is always going to be just R2. It's not going to be multiplied by any numbers. And then R1 is going to be multiplied by something. You'll always have that minus, and then the result will be written as the new R2. So what decides which number goes into the square? Well, that's decided by the operations in the first column. So we want 3 minus this square, whatever is in that square, times 1 to equal 0. That's the idea. We want to eliminate under the pivot. So now it's very obvious that that number must be a 3. So right away, we have the first equation. We didn't say any changes need to be recorded in the first equation, which means we just copy it. 1, negative 2, 1. And then in the second equation, we have a 0 in the first position, which is what we wanted to get. Then we have negative 6 minus 3 times negative 2, so that is a 0 again. And then we have 11 minus 3 times 1, and that's an 8. And this is a big problem over here in this row. Why is it a problem? Because if we try to write an equation from here, this would be 0 times x plus 0 times y equals 8, which is impossible. So this means that the system has no solution. The two lines do not intersect. And another way to say the same is the system is inconsistent. So this expression inconsistent corresponds to having no solution. Okay, that was the first example of a breakdown of elimination. We try to do things as planned, but we can't solve the system. The second way in which elimination can fail is where we don't have just one solution, but in fact we have many solutions. Or, well, in fact, for linear systems, you either have a unique solution or no solution or infinitely many solutions. You can never have just two solutions. It's either one or infinitely many or none. Okay, let's go into writing the augmented matrix. So we have 1, 3, negative 2, negative 6. The vector b is now 1, 3. We have our rows R1 and R2. The operation, well, we know it's the same as before because this is the pivot and we want to eliminate under the pivot. So we have R2 minus 3R1 into R2. What we get is 1, negative 2, 1, no changes in the first row. Then we have 3 minus 3 is 0. Then we have negative 6 plus 6, that gives us another 0. And then we have 3 minus 3 gives us another 0. So now the second row doesn't give any contradictions. It just says 0 equals 0. That's not a contradiction, that's fine. So what's going on now? Well, what we realize is that the two equations that we have over here don't really give different pieces of information. In fact, the second equation, it is really just 3 times the first equation. So then, for any choice of y, we can find an x, and that's how we get infinitely many solutions. For any choice of y, we can find an x. In fact, the solutions to x minus 2y equals 1 give a line in R2 or in the plane. Okay. The third situation in which elimination can fail is if we have a 0 in a pivot position. It usually has a very simple fix. So if I write the matrix, the augmented matrix for the system, I have 0, 2, 4, 3, -2, 5. And I have a problem because I cannot have a 0 in the pivot position. So 0 is not allowed in the pivot position. So what can I do in this situation? Well, I've written we can exchange rows. Why can we exchange rows? Well, if you look at the system here, what changes if I were to write the second equation as a first equation rather than the first one? Nothing really. It's still the same x's and y's that are going to solve the system. So if I just replace the first and the second row, nothing changes in the system. So I can do that operation. I'm going to denote that operation by saying R1 goes into R2 and R2 goes into R1. So that arrow goes both ways. So now my new matrix is 3, -2, 5, 0, 2, 4. And in fact, in this case, elimination is already done. My two pivots are 3 and 2. I can now apply back substitution to solve the system. And just to give you one more example of back substitution, we'll write the system here. So 3x minus 2y equals 5, and then 2y equals 4. Back substitution says start at the back or start at the bottom. So first solve 2y equals 4. From there, we know that y must equal 2. Now use this y equals 2 and replace in the first equation. And there we will get 3x minus 2 times 2 equals 5. So that tells us that 3x must equal 9. And from here, x equals 3. And we have solved the system. All right, more in the next video.